Let's continue with a couple of examples. Problem 1 on page 22. Our entrepreneur, Kenny C. McCrack, owns 12 hip hop, hip hugger fashions stores, specializing in the Full Moon line of gravity-defying lowrider pants. Each store maintains its own inventory of clothing items. Kenny just finished a full audit. It's a census. And the value of the inventory in thousands of dollars is given by the following. So here I have a census, our first census. And it's my 12 stores. Take the data, sort it. And we see right away that 85 is the mode. We got 12 in the population, so we go down 1, 2, 3, 4, 5, 6. And it is between 85 and 86 would be the fold of the data. So the median would be 85 and a half. Add them all up, divide by 12, and you get the mean is 86. There's maybe a slight skew to the right, very, very slight, because the median's a little bit less than the mean. To find the measures of dispersion or variability, we take each observation, subtract it from and subtract the mean from it. Two ways to get rid of a negative sign. One is to take the square of it. One is to take the absolute value of it. When we take the square of it and find that average, we get the variance. When we take the absolute value of it and find its average, it's called the mean absolute deviation. All right, so that's how to calculate those. Easy peasy. Here's a histogram for the census, and there I guess there is a little bit of a skew to the right. We describe that as not quite symmetric, a little skew to the right, unimodal. Yeah.
How do we know we don't 6 down?
Where?
You said 85 is the mode, and then you calculate 6 down.
I calculated the median.
You counted 6 down.
Yeah. Okay. So there's 12 in the in our population. Mm-hmm. Okay. So it's going to be right between 6 and 7. It's going to be this halfway point. Okay. Got it? If it's an odd number, then it cuts right through the middle one. The middle one is the median. All right. If we were to do a plot of the cumulatives, less than or equal to's, then you get a curve like this, and this shape is called an ogive curve. A stretched out S like this is called an ogive shape. On the histogram, okay, so how we read this is there was 1 greater than or equal to 80, but less than the next tick mark, 82. There was 1 greater than or equal to 82, but less than 84. There was 4 greater than or equal to 86, but less than 88. Okay, I read that wrong. There's 4 greater than or equal to 84, but less than 86. So in the spike here, it includes 80, but doesn't include 82. All right, so Kenny's got a potential buyer for the product. This person takes an independent study, doesn't want to spend money for a whole audit, so does a quick sample. Sample is size 5, and I show you how to find the mean, median, and mode again. Mode is 88. Median, since there's 5 in our sample, cuts right through this middle value, 88. Add them up, divide by 5. 87 is your sample mean. And I show you how to do the range and the variance and the standard deviation, just show you the calculations for those. All right, on problem 3 on page 22, carcinogen sampled the amount of mercury in swordfish at 11 different fresh seafood markets across Los Angeles. Got the following results. So we have 11 observations. I sort the data. Find me the median. Right there. Cuts in half, odd number. Let's treat this group here, this first 5, as another sample. Where's its median? That would be the 36, right? That's Q1, sorry, first quartile. And if we treat the second group of 5 here at the end and find where the fold would be there, it would be on 56. So there's Q1, Q2, Q3, 9 and 90. That's what's called the 5-number summary. Give me the 0 percentile, the 25th, the 50th, the 75th, and the 100th. Okay, you don't get how to get these numbers? Is that the question? All right, so I'm given these 11 numbers. The halfway point will be the 6th number, 1, 2, 3, 4, 5, 6. That would cut the data right in half. That's the median. Take the top 5 observations. Let's say they're a sample by themselves. What's the median of that group? 36, halfway point. Take the last set of 5 here. Find me the median of that group. 56. Okay. So when I give you the number 9, 36, 45, 56, and 90, that is referred to as the 5-number summary. And it is the 0 percentile, the first percentile, first observation, the 25th percentile, the 50th percentile, the 70th percentile, and the 100th percentile. That's what the 5-number summary is. Yeah.
If it were an even number of
Then you'd have
12,
to,
it would be split like between 45 and 46.
yeah, it'd be 45. And then you would
include the 45 with the top.
yeah, maybe you would, yes.
5-number summary is 9.
36, 45, it's written right here, 5-number summary. All right, so if I take this data, another way I can convey the results of this data is with the stem and leaf. I have the number 9 as my lowest observation. I have an 18, a 36, a 39, and a 39. And if I put a 9 here, 8 there, a 36, a 39, and a 39, get what I'm doing? So in the 30s, what did I see? I saw a 36, a 39, and a 39. In the 40s, what'd you see? A 45, a 46, and a 47. In the 50s, what'd you get? 6 and 7, 46 and 47. Okay, that's called a stem and leaf. If you have like a couple hundred observations, it's a good way to do it. Because if I were to transpose this, flip it on its side, what do I got? I got a histogram. A histogram with actual numbers. So not only am I conveying, where the numbers were, I'm conveying the actual numbers to you. So it's you can say it's an improvement on the histogram. And then the last thing we need to know about is called the box plot, sometimes called the box and whiskers plot. And what we're doing in the box and whiskers is trying to find outliers. There was a book written about 20 years ago called Outliers. written by Malcolm Baldrige. He later wrote Tipping Point, a couple good books. And he studied people that were truly exceptional in what they did. And the book is called Outliers. 10,000 hours. 10,000 hours. Basic rule is you want to be good at something, practice at 10,000 hours and you'll be good. That's, okay. That was the commonality of all these exceptional people. What we're trying to do in the box plot is to identify outliers. These are people that we think are suspect. They may not be a member of this population. You know, they might have some attributes that make them different than what we're trying to study. So if you go from Q1 to Q3, from the 25th to the 75th percentile, that's the box. That's this distance here. That's the box. And we grabbed what? 50% of them are in the box, obviously. 25 to 75, 50% are in the box. Then from the box, we extend some branches. They call it a whisker out to the right and a whisker out to the left. And the width of that whisker is 1.5, whatever the distance, the width of the box is. Whatever the width of the box is here, which is 20, you extend it 1.5 of those, 1.5 of, what do we call it? The interquartile range, I think it's called. Look back on our, where am I going? Here's where I want. The whiskers go from Q1 minus 1.5 times the interquartile range or distance, and a Q3 and go out another 1.5 times the interquartile distance. That's where the 1.5 is coming from. So 1.5 times 20 is 30. So the whisker would go out from 56 all the way to 86. And the 30 subtracted from 36 gets us over to 6 here on this end. So is there anything beyond the whiskers out here? Yeah, there's one, the 90. That is suspect. That is an outlier. First thing we do with outliers is we retest them. Maybe we had some instrumentation failure, we measured something wrong. There's a problem. Okay, if your measurements are good, then we suspect this individual is an alien of some kind. It doesn't belong to this population, you know, maybe, don't know. It swam over from Japan, you know, it got some radiation there or something. But I guess that wouldn't affect the mercury. But so it's suspect. Being an outlier is not necessarily good or bad. I mean, if it's something exceptionally good, then you're a good outlier. If it's something bad, you're a bad outlier. So again, the box and whiskers plot is a useful mechanism to find outliers. After, what was it, A-Rod's last couple of games for the Yankees, you know, he had a really good finish. It was A-Rod, right? He had the great finish. Who was it retired and then had a really great several last games? Anyway, a bunch of nerd statisticians thought it was a fix. And they tried to prove it with the box plot that it was an outlier and it was, you know, wasn't a normal performance. Another conspiracy theory. Okay, so what the outliers correspond to, if it were a normal curve, which it wasn't, was the outliers are almost plus or minus 3 standard deviations away from the mean on a normal curve. Almost 3 standard deviations. All right, so let's go ahead and figure out the stuff we didn't do. Let's go back and just go down the list, make sure we got everything. Yep. We've done everything there. Okay, sampling methods. We talked about with replacement, without.
I have a question.
Yeah.
Where did 1.5 come from?
It's just the formula. The formula says 1.5. It's in the formula. So we gave you an example of simple random, and we gave you an example of systematic. I'll show you stratified, and I'll show you a cluster here. Okay, if we take our population and we break it down into strata. Strata, of course, comes from geology term for layers of earth, strata. What we try to do is to pick stratifications such that everybody in the first group, the first strata here, looks the same. Everybody in the second strata looks the same in regards to whatever it is we're trying to predict or study. Strata 3, they all look the same. Strata 4, they all look the same. If we did a perfect stratification such that the standard deviation within the first strata is 0, everybody's identical. In strata 2, everybody looks the same. The standard deviation within the strata 2 is 0. And so on. You know, even there's a couple million people here. I could do a census by taking a sample of 4, 1 from strata 1, 1 from strata 2, 1 from strata 3, 1 from strata 4. Okay? But we never get that. If we're lucky, these standard deviations within the stratas are smaller, much smaller than the standard deviation of the population. In which case, if I sample a little bit from strata 1, strata 2, strata 3, and strata 4, we get more accurate results than a straight random sample. Typical methods of stratification are what? Gender, of course, age, you know. Advertisers are looking for that, you know, that magic, age group, you know, that buys their product. Income, region of the country, and things like that are ways that we can do stratifications. When you buy a product and you register the product, they tend to ask a bunch of questions that don't have a whole lot to do with your use of the product, and those are ways of trying to get stratification on, you know, who's buying the product. So if you can do a stratification, you get a more accurate result than a regular old sample. If you can't, then rely on a regular sample. Cluster sampling, in the old days before the internet, when we'd go out and have to study many sections of the country or an area, what you would do is you'd break the map down into little cells, each with the same number of people in the cell. You don't try and group common people at all. It's just random groups. And then a cluster sample, you go out and randomly pick the clusters you're going to study. So you'd pick 5 or 6 clusters you're going to go to. And then you randomly select people in that study. People to be studied. Okay, that's our 4 sampling methods. Probabilistic sampling methods. Non-probabilistic sampling methods. Judgmental. We build a group that we think is representative of the population. It has the exact same percentages as our population, as far as, you know, male, female, age, all that. And they say, this group represents the population, I will sample this group. It's great in theory, but you cannot make any statistical statements, no probabilities whatsoever regarding that result. That was the knock on the Nielsen ratings for all the years, is because those families were selected based upon their characteristics, not randomly selected. So they could never prove that their surveys were correct. A convenience sample, that's a dating strategy. That's not a sampling method. You can take whatever you can get. And it's also It's also the method of sampling on the internet, you know, where people just voluntarily respond, which is extremely inaccurate. Again, that's the last one. It's the voluntary response or the self-selected. That's what you get on the internet. Okay, with non-probabilistic sampling methods, you cannot make any statements of how accurate they are at all. Okay, what kind of errors do we have? Okay, random sampling has basis in there that, you know, we had variability within the population, so we're going to have variability in the sample. And those sample errors are built into our probability statements we're going to make in the rest of the semester. And you know, regular sampling errors where sampling error is where the sample doesn't exactly look like the population. That's a sampling error. We are going to be able to account for those and build them right into our confidence interval and our probability statements. Non-sampling errors, though, are sampling bias, okay, non-response bias and response bias, and confounding. A good example of the sampling bias, the classic example given is the 1936 election between FDR and Alf Landon, in which the Literary Digest set out, polled 10 million people across the country, and they got back 2.4 million responses. And they predicted that Alf Landon would win in a landslide. I don't remember Alf Landon being on the dime, do you? No, he's not on the dime. FDR is. What happened was they sampled the readers of their magazine. It's kind of like the New Yorker, a highbrow magazine, you know. And what else did they do? They sampled people with phones. They were easy to sample because they could call them. And they sampled any registered car owner. They could get those easy. So they sent bingo cards to all the people who registered, had a car registered. Well, who are the people who read their magazines, who had phones in those days, and who had cars? They were rich people, that's all. And so it was biased. It was extremely biased, and it was, you know, biased towards sampling rich people. And of course, Alf didn't win. Same election, George Gallup sampled 50,000, not 2.4 million, 50,000 across the US, and did an excellent job and started a business based on the results. He was the modern day Nate Silver. Nate Silver is probably the top forecaster out there now. He didn't call Trump, but he gave Trump the highest chance of winning of anybody, but he didn't call him. So he said he had a, you know, not a better than a 50-50, but he had a reasonable chance of winning, and he called it. He did the best of any of the people who forecast. So George Gallup called almost every state, and they called it correctly for Roosevelt. Okay, here's an example of a response bias and a non-response bias. Well, it's an example of a response bias. Ann Landers got a letter from a woman who, you know, was 60 or so, and said that she devoted her entire life to her kids, and now, you know, she doesn't get any calls or presents on Mother's Day, and they're a bunch of ingrates, and if she had to do it over again, she wouldn't have kids. And so Ann Landers said, let me do an informal poll, and if you have some response to this, please send me a letter. Well, she got back about 90% of the letters she got said, yeah, if I had to do it over again, I wouldn't have kids. They're awful. By the way, most of your parents wrote in. Well, what happened? Who mailed in? The people with rotten kids. Okay, the people who had an axe to grind. The people who, yeah. So then she commissioned an actual poll where she randomly selected people, and she found the exact opposite. 90% of the people who had kids would do it over again if they had to do it again. So that's the response bias. The people who respond to the poll are, have an axe to grind, and that's the ones you see on the internet all the time. So self-selected polls on the internet are worthless. And around election time, you'll get polls that you can tell the sampling bias immediately by the types of questions they try to ask you, how they word the question. They know the result they're going after. A good example of a non-response bias is if you take a poll and ask people about their income. Rich people don't like to let other people know they're rich, and they usually tend to understate their income. Lastly, confounding. This is where we confuse correlation with causation. Okay, so correlation means when one thing increases in value, the other thing increases in value, or when one goes down, the other goes down, or vice versa. When one goes up, the other goes down. So one positive correlation is when I go up, you go up, and when I go down, you go down. Negative correlation is when I go up, you go down. So the value of a bond and the interest rate are positively or negatively correlated. When just interest rate goes up, the value of the bond goes down. If you sell that bond, you're going to lose money if the interest rate goes up. And if you own a bond and the interest rate goes down, that bond is worth more. It's worth more in money. All right, so there's in confounding, we confuse correlation. They move together. They're related with causation. Okay. Now, the case of interest rate and the bond, it is causation because the interest rate went up. That's mainly why the bond's going to go down. But sometimes things just move together. They're related, but they're not causally related. Here's a study. Numerous epidemiology studies showed that women taking combined hormone therapy for menopause, had a lower rate of coronary heart disease. Okay, so women would take hormone therapy to ease the symptoms of menopause, and they found that these women also had lower than average incidence of coronary heart disease. So they found that those women who were on the hormone therapy had lower coronary heart disease. And they thought it was causal. It's not. In fact, the exact opposite's true. They did control studies and found that hormone therapy, if you have a severe risk for coronary heart disease, you better not take hormone therapy because it aggravates it. So what happened? Why did we get this, what's called a spurious result? It is because, what were the attributes of the women who took the hormone therapy? Number one, they had money, they could afford it. And number two, they took care of themselves. They had insurance and they took care of themselves. So that group of people have a lower heart disease rate than other people. So, it was because of that they were getting these results. And then later they showed that the hormone therapy, it was again a heart risk, not something good for the heart. It was bad for the heart. Okay, so practice problems, memorize your symbols. Okay, so next week I'll raise your arms and show me your Sharpie 8 symbols. Memorize those and then practice these problems. Second easiest practice problem set of the semester. Last one of the semester is easiest. Okay, before I give back the exams, let me go over a couple of things. Since I got this one up here, here's the solution for the Jeopardy problem. Okay, where this was you know, what I expected you to do the tree as, okay? We can either bid nothing or we can bid the 10,000, okay? If we bid nothing, okay, then you already know, doesn't matter whether you answer the question right or wrong, you know, you don't even have to look at the question. So I don't care whether you got the question right or wrong, it has no bearing on the problem at this point. We know that you got 10,000 bucks. If James gets it right and Ken gets it right, you're in third place. Okay. If James gets it right and Ken gets it wrong, you're in second place. Second place gets 2,000 bucks. If Ken gets it wrong, James gets it wrong, but Ken gets it right, you're in second place. If Ken gets it wrong and James gets it wrong, you make the 10,000 bucks you had. If we bet the 10,000 bucks and we miss the question, you got zero. You're going to be in last place. End of story. Your third place money. You got it right. If they both get it right, you're in third place. If either of them miss, you're in second place. They both miss, you make the 20,000. So this was what I expected. A lot of you put the two more states here and a bunch more states here, which, yeah, I didn't really think you would do, but we did in the, you know, anxiety of a big exam, which I didn't mark bad, you know, for having more circles, but so that was the one that turned out that I was really disappointed with. And I thought my explanation of the problem would be sufficient on how the game would be played. That, you know, that you get to wager money, some of the money you've earned, and then the one with the most money, if you get it right, you double your money, and the one with most money at the end gets keep the money, and the other two get second, third, whichever place you finish in. So I was pretty lenient on that one, and then again, the 6 points I added is mainly for that one. The other thing is on problem 3, the payoff table. A lot of you treated it like a one-period inventory problem, which it isn't. Okay, one-period inventory, we sell or don't sell, and after that, you know, we can count our money. You can't count your money. If you send bikes back to the shop in Ventura, you can't count your money. You got to wait until those sell. So there's 3 ways to do it when it's not a single period inventory problem. Number one, what we do mostly is we recognize the cost of it when we sell, right? Which is the way I've written the solution. The second way is, if you would have treated it as a sunk cost, that we've already paid for those bikes, I would have given you full credit on that. That would have been a winner. And then all we're looking at is the revenues and additional costs above and beyond that, and any discount that the manufacturer gives me. That would have worked. The other would have worked as if we got them in, but we still have to pay for them, and you net out. Obviously, we have at least 30 of those bikes in Ventura because that's how many we're thinking of taking up. So we already have them there. So one case you already paid for them. Second case you haven't paid for them, but you're going to pay for all 30 right now. Fine, okay. But you can't mix the, you know, where you're charging the fee of some of them, but not all of them. It doesn't work. So I knocked you a couple of points on that. Those are the most commonly missed problems. All right.